So I'm going to be talking now about Kubernetes and how you can be using Kubernetes in short terms. My name is Ted Dunning. You can reach me by email, by Twitter, by guest, by Gosh. We've carefully crafted aliases, so most of the emails that you might guess at MapR will work for me. And I'm happy to talk to anybody. I'll be over at the MapR booth afterwards, and we have a get-together this evening in the Chamberlain Arms. Now, the first fact of life here is that Kubernetes is coming. Now, I haven't defined it yet, so that's going to be a little bit Greek for some folks. But it's an interesting thing. Gartner was predicting that by 2020, half of the top companies would be using Kubernetes in production. Last year, the Cloud Native Foundation did a survey, and they found that 60–70% of large companies were using Kubernetes in production. That was 3 years ahead of schedule. Now, normally, these analysts are kind of hyped and optimistic about adoption of these things. Here, they're the biggest pessimists around. So Kubernetes is being adopted ubiquitously by large companies or people with large compute loads. Let's talk about why. That's a natural question. Why are these people doing that? One is that there's a huge groundswell of community support. These are packages and projects which are supporting Kubernetes. This is not to speak of companies doing it, but there's a vast amount of software that's being adapted for running with or for or to assist Kubernetes. Every major cloud supports it. And in fact, Google, of course, speaks Kubernetes natively. And Azure's container system speaks Kubernetes natively. Amazon speaks it as a very good second language speaker. So everybody supports it in the cloud, and there's lots of minor clouds that support this as well. There's massive customer adoption, and this is not adoption as we're trying it out. It's adoption as in we're committed to it, as in people like SAP saying they're committed to delivering products on it. And soon, that's how they want to deliver all their products. This is big. After why, what? What is Kubernetes? I made a joke a little bit ago and nobody laughed, which means that some people don't know what Kubernetes is. I said it's kind of Greek to some people. It is. It's Greek. I mean, it means the steersman, the guy who's steering the ship. And that's the idea of what Kubernetes does, is it steers a cluster. It orchestrates what's happening in the cluster. It's an effort which derives from the Borg, which was the cluster manager, the orchestrator that Google used to be able to provide their product builders with essentially infinite computing capacity, meaning more computing capacity than they could effectively use. And the Borg is now available in the form of Kubernetes. Kubernetes is an ecosystem, as we mentioned. There's enormous number of projects that work with it and for it. And it is a container and resource orchestration engine. Now, there are others. Mesosphere has their DCOS, which is running Mesos. There's the Docker Swarm, there's Hadoop Yarn, there's other projects that claim this sort of space, but they are losing ground rapidly. The adoption and unification of this market is prodigious. Kubernetes has essentially won it. This is 2017 results. This is adoption. These are smaller than in the CNCF survey that I've seen. But keep in mind that Cloud Foundry and OpenShift essentially are Kubernetes underneath the covers. And so you can see that the second place is actually Mesos back then. And these are not production numbers, I don't believe. So let's talk about what it is. And its single purpose is to run containers. Raises the question, what's a container? Come on. A container is not a VM. Now, there are lots of things that are not a VM. My thumb is not a VM. But this is actually a useful definition because it's a lot like a VM, like a virtual machine, but it isn't. And the big thing that it isn't a VM is that it does not replicate all of the operating system. It's much lighter weight. It lets you have a lot of the isolation in terms of what things have you installed, what fixed utilities are available, which versions of libraries do you use, and things like that. Isolation of that sort. It gives you isolation of which processes are visible and things like that. But it shares the operating system. So each of these containers here, which have their own application and libraries, is sharing the hardware in the operating system. Whereas in the container case, we're replicating a lot of that stuff. That means you can run more foreign things that are dissimilar with VMs. Here, the fact that you're sharing the operating system is somewhat of a limitation, but in fact, it's not much of a limitation because the operating system doesn't have to be very broad. Now, the big difference, though, is not this technical sort of thing. It's the difference between kittens and cattle. Now, I'm only a Texan-in-law, but I can still talk about cows. And the big difference between kittens and cattle is you name the kittens. You give them a name, right? You have a cat? You have a cat? Oh, come now. Somebody's got a cat. Okay, what's the cat's name? You know what the cat's name is, don't you? Anybody got a cow? No. Okay. Well, did I see a hand? No. Okay. Well, this just shows this is not the Midwest in the U.S. because everybody would have claimed to have a cow. In general, unless you're a teenager exhibiting at the 4-H, your cow does not have a name. Your cow has a tag in the ear with a number on it. Kittens, names, cows, numbers. Pets are long-lived in our affections. We name them, we care for them. If they get sick, we fix them if we can. Cows, there's another cow. You put numbers on them. And well, yeah, vets are expensive. That's the difference, right? You're not going to put a number on your cat. That's cat number 3. That just doesn't work. I'm sorry, there was a picture being taken there. Okay, so that's a big difference. The container is this image, this base image, plus isolation. It isolates the CPU, it limits the CPU, it isolates the memory, it isolates namespaces like processes. But the real big revolution is the idea that we don't name them, that we just manage them as a computing fluid, a bunch of things that we can do. Now, containers are really good. In fact, the containers are excellent. Containers are really good for what they do, which is isolate things. They have a glaring and serious problem. The problem is that if you keep them around too long, they turn on you. Even though you've tried to keep them to be cattle, you wind up naming them. You wind up, caring for them. You wind up going in to fix them. And you shouldn't do that. With a container, if it goes bad or if you have a new version, you should just drop that container and start a new one. You don't SSH into containers to fix them. You do SSH into a virtual machine and fix it. VMs are pets. Containers should be cattle. But people start keeping them around. They start using them as cheap VMs. Now, things that Docker, which is supposed to be the container people, don't really handle is they started with this idea of containers as cheap VMs. Whereas Kubernetes is starting with the idea of containers as a computational fluid of you get some more of that or you get some less of that. It's always multiple containers, and you don't really care which ones, and you don't care if they come and go. So Docker doesn't solve the issue of naming, doesn't handle monitoring, doesn't handle dead containers. It doesn't really move them around to improve multi-tenancy. Instead, what we need is something that does all of that, and that's what Kubernetes is doing. This is kind of the magical high altitude view of it. But the idea is that Kubernetes will start an application which consists of many containers arranged, and we'll talk about how they're arranged. It will start them somewhere in the cluster. It'll start another application somewhere else. That else might be close if you say that these two applications have an affinity, or it might be far away if you say they're both heavyweight and they have an anti-affinity. Application 2 may start as well, and these provide services. And one of the most important things that Kubernetes does is it allows you to also name these services and access them by name. Okay, so we've got the idea of computations as groups of containers that are positioned to use resources well, to keep the utilization high, to improve multi-tenancy, and to name them. Now, we didn't say which machine it's going to run on, and in general, you have no clue about which machine your code is running on with Kubernetes. You don't name it. You don't have to think of all of the characters in The Hobbit and come up with a different name for every computer that you're going to have a real affection for. We used to do that. It just isn't done in this new world. They're cattle. You got some more, you got some fewer, you take them to market. Now, this has led to a huge change in software engineering, a huge change in how we build software. The idea is that software development goes in stages, and at its stage, we remove the right to change things. With source control, we freeze the source code. You're not allowed to just hack it after you check it out if you're building for a deployment. After the compiler runs, we're not allowed to change those bits. The binary is the binary. After we package it together into a container, you're not allowed to mess with it. You don't SSH in and upgrade a package. Each time, we are removing degrees of freedom. And this is kind of the story of computing. We remove the go-to, we remove degrees of freedom, and we get more power as a result. With this kind of discipline, things become easier to build. Here's a picture. With Git, we control the source code. We check it in, it is frozen, it is versioned, and we control it. We compile things. Once upon a time, I kid you not, person would change the running bits in memory of a program as it was running. It's like, because you had to. You don't have to do that anymore. And going in and changing the contents of a VM is the same thing. We don't do that anymore. Do we? Okay, we don't. So we don't change that. And now we've got containers. And so we package configuration, resources, libraries together into a nice multicolored block. And that becomes our container, which has a frozen configuration. But there are two more steps that we need. One is we need to be able to describe how to arrange these containers with some free variable still, but we're going to say our service has these kind of containers up here. I don't know how many. They're going to be connected to these containers down here. I don't know how many. The thing that connects them, I don't really know yet. But I know they will be arranged like this and connected like this. And then there will be some stuff below that they store data in. But I don't know where that is. So Helm is the Kubernetes package describer, system describer thing, and Helm package is the command that does that. And then we deploy it, and when we deploy it, we insert keys and secrets and certain configuration. We insert the load balancer and we attach the storage. These are slides stolen from Eric Brewer, who's the head of infrastructure at Google. He's also the guy who wrote the CAP theorem, which is kind of an amazing thing for an IT guy. So this is the way we build software now, and this is glorious. This is wonderful, but there is still a very bad problem, and it relates to the problem before. The problem is state. If you put state into a container or into a system and lock it in, the container assumptions go away. The idea that you could just kill a container and restart it somewhere else goes away. the whole fluidity of the process goes away. And that makes it really, really hard to manage these systems. At least once you violate the assumptions that Kubernetes is based on, Kubernetes doesn't really do what it's supposed to do. That state there messes all kinds of things up. It makes things heavy. Data has mass, data has inertia, and we must live in a very fluid world if containers are to work. So let's talk about what a service is. A service is a thing you make requests of. Traditionally, it's an RPC. You make a REST call or something like that. But that's not all that it could be. That's a synchronous service. But you could have deferred work. Please, just do this at some point. I don't care when. You know, here's a sale, account for it tonight. That's a deferred thing. That's an asynchronous service, and that's what streaming architecture is about. So the stream could have a synchronous request, and then it could defer some of its work out through a stream. Now, one of the things about that is that it hides things. If I hide the details of who and where things are, I have a service. If I hide the details of who's deploying what and when, I have a microservice. If I hide the details of when, if I hide the details of time, then I have a streaming microservice. And these are nicer and nicer. The idea of streaming microservice is a producer puts things in a stream and doesn't really care. It's done. The stream has responsibility. Notice the consumer doesn't even exist here. That's the temporal isolation. Time is no longer locked between the producer and the consumer. The consumer has freedom to run whenever is right. And indeed, the consumer may not even exist yet. That's the ultimate freedom. The implementation detail. Have you finished the code yet? Well, I'll get to it. Now, that consumer may exist and may run whenever is appropriate after the data is inserted, but that consumer could also be very, very far away. That's the geographical isolation. So streams give us that. Now, this ultimately means that we have more than just files that are important to us. We need tables because tables are better than files at a certain scale, but we also need streams to connect these asynchronous services together. So now let's finish this diagram. This is where we were before. Kubernetes is magically positioning this software, managing it within a cluster, but it is not managing state. And the applications should not have state. They can communicate via that RPC link. That's a synchronous link. But they also need to communicate via this persistent stuff down below. And that persistent stuff has a different life cycle than any of the applications. So it should not be in any of those applications, and it should not be in ordinary containers either. What we need is a data platform. A data platform which is the analogical dual of what Kubernetes does. We need that data platform to position data, to move data around as necessary, and to name it. Just the same way that Kubernetes positions these processes inside a service, moves them around as necessary to maintain multi-tenancy, and names them. They are exactly the same services, that things that are provided that Kubernetes does for containers need to be done for the data. Needs to have a namespace that spans across an entire Kubernetes cluster and even beyond. It needs to have all the forms of persistence essentially built in. It needs to be inherently scalable so that nobody really cares how big it is today because there are no visible limits. It needs to be scalable in multiple ways: performance, size, cardinality, diversity. It needs to have uniform access and control because the IT organization has to manage this at wholesale. The IT organization is not allowed to say, oh, you're going to run 10 times as many apps, I'll need 10 times as many people. The fundamental theorem of IT management is you have a relatively fixed team size and you just buy more hardware and manage it with the same level of effort. At application level, you manage things at retail. You know how many files there are. You know about each application. That's a different thing. Your data platform has to provide that line. It just so happens that I work for a company that has that, had that for some time. We knew this was going to happen. We just didn't know it was going to be Kubernetes. And so you can now wire this up. This is a specification for a service. And if we magnify this horrible font, the last part of there is saying, glue this driver into a volume path here, and here are the security tickets. This gives you access. So normally you would have kubelet managing these Docker containers arranged in a pod. Now what you get is a sidecar container, an additional container that is glued onto the side of your container, and it provides access to this generalized file system. That lets you build these services with Kubernetes above and a data platform below. It allows you to build these services with no change to this application container, which says Docker there, but it's where the application actually runs. You can take something off the web, MySQL database, plug it in there with no changes, no modifications, no adaptations, and these now run transparently. So where does that take us? That takes us to some consequences. One is, this is a platform level rollout. You don't have to change any of the containers. You don't have to change the per node configuration. Kubernetes is going to manage the plugins. It's an overlay so that no container needs to change. We can share storage and compute, or we can isolate them, or we can scale them independently. It really, really is pretty cool. State is no longer a dirty word at that point. It's an easily managed commodity. High performance computing works great in this kind of environment, especially the mesoscale high performance computing that a lot of people are doing with GPUs using things like NVIDIA systems. Previously crazy stuff is now actually pretty dead simple. The complexity of this is not visible. That's why it works. So container orchestration is fantastic. That's what Kubernetes does. Data orchestration is just as cool. So here's some examples. Now these happen to be MapR customers because those are the customers I know. So if you just hook up your system in the storage container up above to a cloud, you get a certain kind of plug. That is that cloud's API. If you try to run with other clouds or on-premise, your plugs will not match. It's like Americans visiting Europe. Nothing plugs in, except one place. That's in the Hotel Shaver. Okay, so that's the state as it is with nothing else added. But if you add a clean data layer, this is developed by our German team, that's why it has that plug. But you get a set of open APIs, standard file access, standard stream access, standard table access. That means that you can now unify multiple clouds, internal and external resources. You can now make the clouds be, the cloud providers be commodity players. They are selling you a replaceable commodity, not a unique jewel. That gives you a uniform computing everywhere. There's a manufacturing company here in London, and they're able to have multiple clusters in manufacturing facilities, and they get the same data layer to move data uniformly from facility to facility, accessible in every place with the same APIs, exactly the same code, and they don't care if it's in a tiny little edge computing thing, in a traditional data center, or in any cloud vendor. It all just works. All of the data just moves transparently. That gives you platform level data replication. Another customer, a big bank, is able to use this global namespace so that they have a part of the namespace for each office. They need to do a lot of compliance work, and so each particular office needs to keep compliance data in that jurisdiction. But they need to be able to access it globally, act locally. They can now do this because they can see this data no matter where it sits with exactly a global, perfect, universal namespace. They can access it anywhere. Another company is building a universal application platform where they have applications that need to run different times, different ways. They can scale them, they just set a few parameters, and they select how and where they want to run, and data moves with them so that they are provisioned as they run. That gives them a compute fluid that spans across multiple companies, multiple data centers, multiple countries. And they don't really care other than sometimes it costs more, sometimes it's closer to the data source. It gives them a single pane of glass to control their jobs anywhere they want them. And we have books that we've been describing our view of how these architectures should work for some time. We had a book about machine learning logistics last year. Before that, a book on streaming architecture, which talked about this idea of asynchronous microservices. These are all available for free PDF downloads. They're published by O'Reilly. We make them available free. We also have books on machine learning, practical machine learning. Speaker before me was talking about recommendation engines, how amazingly difficult they are. In fact, they can be made quite easily with nearly the same performance. That's the Pony book down there. Anomaly detection, you can also do very, very straightforward approaches for that. That's the fish book. One of the fish is backwards. It's an anomaly. We also have a more recent book, AI and Analytics in Production. We had a book signing today. A ton of people had books. And we'll have another book signing tomorrow, 1 o'clock. We'll be giving away free copies of this, real physical, Stone Age type copies of books. You can also download this one for free in PDF form. Yeah, well, I remember when we didn't have dirt yet. We just had rocks. It was an old age. You can contact me. My name is Ted Dunning, T.Dunning at MapR, T.Dunning at Apache, ted.dunning at Gmail, any way you like, or you can catch me now or at the booth later. And if there's any questions, I think we have 2 minutes to go. Are there any? Should we adjourn? Are you wiggling or are you asking? Wiggling, okay. We have one for wiggling. Two, we have another wiggler, but no questions yet. Okay, then thank you very much.